parameters as one way of as one of the methods of measuring flow rates. So today we are going to look at another application of Bernoulli's principle, and that is flow through orifice. Flow through an orifice. Now consider that we have a tank with a small opening at point number 2. A tank with a small opening at point number 2. Can we mute our mics, please? Let's mute our mics. So the figure on the right, shows how the streamlines would be. Okay, if you could look at the next slide. Do I go to the next? Let's look at that slide. Typically, that's how the flow patterns would be if you have such openings on the side of a tank, or if we have a similar structure, such a structure obstructing flow in a pipe. If you put it in the path of flow, if you put it in the path of flow for purpose of measuring discharge, you can put that structure for purpose of measuring discharge. So that's how those are the typical flow patterns, how they would be. Okay. So the streamlines, like you can see, the streamlines at the start, let's see, ballpoint pen. You see, at this point, they are diverse, but they tend to concentrate just outside the tank. Same with this here, they are converging, and here they are straight. Okay. Likewise, here we have the streamlines converging. Now, I don't know who's disrupting our class. Please mute your mics. Please mute your mics. Okay. So the streamlines contract after the orifice a minimum value, and at that point they become parallel. Now at this point, the velocity and pressure are uniform across the jet. Now that point of convergence is what is normally referred to as the vena contractor. Now it's important that if you're going to determine discharge, you determine it at that point where the streamlines are converging, where they are parallel. That means when there is some uniformity in the velocity of flow. So Bernoulli's equation can be used to determine the velocity at the orifice. And that way we can determine the discharge through the conduit or the discharge from the tank. Now, if we can refer back to our figure there, the figure on the left, let's take a streamline from point 1 to point 2. Remember we said Bernoulli's equation applies on the same streamline. So if you consider a streamline that cuts through point 1 and point 2, where point 2 is at the orifice. So if you apply Bernoulli's equation, we can say P1 over rho G plus U1 squared over 2G plus Z1 is equal to P2 over rho G, where P2, the terms P2 denoted by 2, are the conditions at the orifice. Now from this we can say U1, we can set it to 0 because U1 is at the surface of the water. U1 is at the surface, is the water surface. So U1 is approximately 0. Okay. Secondly, the water tank, this water tank is open to the atmosphere. And since we are dealing with gauge pressures, so we are going to say P1 is also 0. So that means we cross out this and this. Okay. And then we remain with Z1 is equal to P2 over rho G plus U2 squared over 2G plus Z2. Now, the orifice is also open. If you look at that tank, the orifice is also open to the atmosphere. So it's also open to that atmospheric pressure, which is at gauge pressure 0. So P2 is also 0. Okay, so we remain with Z1, we get a pen. Z1 equals to U2 squared over 2G plus Z2. Now, if we take any datum, assuming that maybe my datum is, okay, assuming my datum is, okay, take it to be straight. Assuming my datum is here, okay, so Z1 would be this, Z1, and my Z2 would be that, Z2. Now you can see that the difference between Z1 and Z2 is H. So if I have Z1, if I rewrite my equation, it says Z1 minus Z2 is equal to U2 squared over 2G. Then Z1 minus Z2 is H. So H is equal to U2 squared over 2G. And then we'll get U2 equals 2GH, the square root. Okay, so we have U2 as root 2GH. So that is the theoretical value of velocity at the orifice. Now, usually there's a coefficient of velocity that is used, just like with ventilometers. We talked of a coefficient of discharge to correct the theoretical value that you have gotten. Even in orifices, there is a coefficient of velocity that you have to multiply in this U2, okay, to get the real velocity. So actual velocity is equal to the coefficient, is equal to the CV, coefficient of velocity, times the theoretical velocity. Now, most orifices, like they are noting there, most orifices range from, have a CV that ranges from 0.997 to 0.99. Okay. Now, to get a discharge through the orifice, from Q is equal to AV. So Q will be equal to the A times velocity. But in this time we have the velocity is given by CV times U. Okay. Now, how do we get the cross-section area A? The cross-section area A we are talking of is the AV, the A that we are talking of is the A at the point of contraction. Okay? At the point of contraction. So actual area of the jet
area of jet.
Actual area of the jet at the point of contraction is equal to the area of the orifice multiplied by the coefficient of contraction for the orifice. The coefficient of contraction of the orifice. Different shapes of the orifice edges are going to give different areas of contraction. So Q is equal to A naught CC, okay, times CV times U, okay. So then we can say the actual discharge is given by CC times CV times A naught times U. So Q actual is equal to, now CC times CV becomes CD. Now a given orifice shape has a particular coefficient of discharge, but that coefficient of discharge is coming from the coefficient of contraction and coefficient of velocity of that discharge, so of that orifice. So we CV, that's a constant that can be denoted by CD now, combining the two terms, then times area of orifice, then root 2GH. So that's it. That's how we can use Bernoulli's equation to determine
What?
Discharge from a tank or discharge through an orifice. I hope we are together up to that point. Are we together?
Yes.
Now notice here we set P1 and P2 to 0 because they are open to the atmosphere in this equation. Because they are open to the atmosphere, we set them to 0. So it means that if they were not open, to the atmosphere, assuming that this was a closed tank, with a known pressure force here, it could be a pressurized tank. So our P1 would not be 0. Our P1 would be the pressure at that point, exerted at that point. Likewise, if this orifice at number 2, at point 2 was not open to the atmosphere, then we would have the pressure that is exerted at this point. So for example, if the orifice is submerged, say if the orifice was submerged, that is if we have two tanks next to each other, then we would have, okay, still applying the Bernoulli's equation to a streamline that starts from the surface here up to point number 2. If this is 1 and this is 2, then we have P1 over rho G plus U1 squared over 2G plus Z1 is equal to P2 over rho G plus U2 squared over 2G plus Z2. Okay. Now, in this case, the first tank is open to the atmosphere. So P1 is equal to what?
0.
0. Secondly, U1, that is a surface, That's the free water surface. U1 is approximately 0. So we have this and this cancel out. Then is U2 open? Is U2 open? What about U2? Sorry, P2. What about P2? You see, P2 is at this point, which is in the second tank, and it is experiencing, it's at a pressure which is caused by this column of fluid above it. Okay, so the pressure at point 2, is given by the height of the fluid column above 2. So which is given by H2 rho G, which is called H2 rho G. So U2, of course, is the velocity that we are trying to determine. Now, likewise, the difference in height. Okay, if I put my datum here, the difference in height between point 1 and this point 2 is actually this H1. That's the difference in height between point 1 and point 2. So if you take this Z2 here, so we remain with H2 rho G over rho G plus U2 squared over 2G, which is equal to Z1 minus Z2, which is H1. So we'd have it that way, and then we can say U2 is equal to the square root of 2G into H1 minus H2. So likewise, you consider the coefficient of velocity, consider coefficient of contraction, then to have the discharge through the orifice, in this case, as CD, coefficient of discharge, times area of the orifice, times the velocity, which velocity in this case is 2G into H1 minus H2. Okay. I hope we are still together. Are we still together?
Yes, we are.
Yes,
Good.
we are.
So that's about orifices. That's about orifices. Now, the other way of determining discharge, or the other application of Bernoulli's principle or equation is through notches and weirs, determining discharge using weirs and notches.
Excuse me, sir.
Yes, please.
Before that, on the orifice, how would you account in case the orifice was discharging into the liquid of different densities? They
Sorry?
assume, let's say this orifice, the orifice is discharging into the liquid of different density. Let's say the liquid of area A2 is different from the one of A1.
Already we have a density term which will take care of that. Hello?
Hello.
Hello?
Hello.
Hello?
I'm hearing. Yes, sir.
Now, if it is a hello?
Yes.
If you're talking about now, if you say different densities, now are we still talking about the same streamline?
I think so.
I don't think so. because remember, there's one of the assumptions that we talked about. We are not considering friction. Now, when you talk of different densities, then you're bringing in friction.
Yes.
We are bringing in friction, so that it becomes analytical. Okay.
Yeah.
So for now, it is we can consider that to be out of our scope. But if it's a fluid of different density, then this principle about the vena contractor may not work, because that's a different density. And once it's a different density, that is flow now against friction. That is flow against friction. The approach may be different. So I believe this theory, if you introduce another fluid, then our assumptions may not be valid. Okay, but in terms of the pressures that are involved, we already have a density term, so that density term will take care of the other fluid. But in actual sense, the moment you introduce another fluid, especially if it is thicker, then you are going to have then probably the vena contractor, the principle of vena contractor may not work, because you're flowing under. Now you have a flow against friction. Yeah, but I can leave that as your homework to read more about that. But remember, we are using simplifying assumptions, and the moment we are trying to idealize situations, but otherwise, you know that the situations in nature are a little bit different. They are complex. Okay. Any other question? Okay. So the other application is on notches and weirs. So a notch is an opening on the side of a tank which extends above the surface of the liquid. For example, if you have a tank, if I have a tank, let's say, if I have a tank, let me draw it on the side. Okay, assuming this is a perfect rectangle. If I have this tank, and then I come and cut a V slit here. Okay. So this goes off. Do I have an eraser? Let's see. Is there an eraser here? Okay, I can't get an eraser. It's not active. But if I cut an opening here, I've cut a slit. So that means this line is not there. Okay. Okay, it can be there because you're seeing the from your drawing. Of course, it can be there because you're seeing the line behind. But assuming that you're not seeing it, I want you to see this slit that has been cut. So this opening would be this is an opening. Of course, if you cut a slit, if the tank was full, then you have water flowing out of the tank through here. It would flow out until the water reaches this level. That's when it stops flowing out of the tank. So in this case, assuming now, take a snapshot when water has reached this level. Okay, you just cut it, you open it suddenly. So water starts flowing out. Now take a snapshot when water has reached at this point. Now at that point, we have an opening that is extending above the surface of the liquid. Because we have this opening here where the lower part is still submerged in water, but the upper part is extending above the surface of the liquid. So this is what we would call, in that case, that would be a notch, right? Then a weir is also a notch, but now on a large scale. It's a notch, but on a large scale. Can you mute, please? Can you mute? Who's disrupting us? Please, if you're in a noisy place, mute your mic. Hello? Godwin, you're disrupting our class. Godwin, I'm going to exit you. You're disrupting our class. Thank you. I think he has decided to quit. Okay, so let's proceed. I hope you're still seeing my screen. Are you seeing my screen? Hello?
Yes.
Okay.
Yeah.
I can see us.
Saying it.
Okay. So we said now, what do we mean? Let's go back to this illustration. It has gone off. Where are my things? Okay. You see, if I cut this slit here on the side of the tank, okay, when I cut here, this opening, this notch on the side of the tank, assuming you have these normal tanks that you have at your homes, it has a very small thickness. So if I cut it, it means that notch is sharp crested, or I could be having, I can have a V-shaped or whatever shape. It can be rectangular, it can be square. I can have, okay, let's assume that I've taken, let's assume that I've cut off this side of the tank here. You're not seeing my screen? I thought I shared the screen. Yes, I'm writing. Okay, let me use a different color. So I'm saying if I cut, you see, if I cut this part of the tank here, and I take it with this notch, okay?
I'm seeing nothing.
Still can't
Put on
see.
specs. Put on specs.
You can't see what you're
Okay.
writing.
You can't see what I'm writing.
Yes.
Yeah.
Okay. Now, assume that you get a flat cardboard. At least, do you know a cardboard? You know a cardboard. So assume that you get a flat cardboard and cut a V. You cut a V off on the cardboard. Okay. Now, then you take that cardboard and put it and place it in a stream to obstruct flow. Now, when you try to obstruct flow, you're going to have water rising up, and the first point at which it will come out will be at the tip of the V. Not so. If you obstruct the flow with a cardboard, you have a cardboard where you've cut a V or you've cut an opening. So the lowest level of the opening, that's at that point, that's where the water will start coming out. Now, as I'm obstructing that flow, if it is at a large scale, if it's a stream, what I will have created is a weir. But that weir, because I've just cut in a cardboard is thin. Just because I've put a thin cardboard, then we can say it has a sharp crest. We say it has a sharp crest because at the point where the water comes out, the thickness is small.
You saved on desktop.
Sorry? Sorry?
This is the one.
Sorry?
We cannot see your illustration.
I was trying. I hope that you would imagine. Okay, let me give you this picture here. You can see this picture? A? Can you see A?
No.
It's on the screen.
No.
Are you seeing my screen?
No.
The screen is of notches and weirs.
The screen has frozen.
How about now?
No.
We can't see.
Let me share again.
No.
Let me share again. Let me share again. Can you see now?
Yeah, perfect.
Can see now.
Okay. Now, on the left-hand side, it's being used as, that's a V notch. Or in this case, at this point, since it's on a large scale, because this is on a stream, it's a weir. Okay. So if you look at this is a V, but it is closed. If you remove that opening, sorry, if you removed that, if you removed the cover, okay. If you remove this cover here, this one here, the gate, if you open that gate, water would gush out through this V. Okay, it would gush out through. It would gush out like this through this V. Now, because along in the direction of flow, because this is a thin plate, we say that the crest is sharp. The crest is sharp because we say the crest is sharp because this plate is thin. Now, assuming that instead of putting a thin plate, assume that in case of putting a thin plate, somebody put, you see, you have a box like, if you have a, you can make a V in a box like shape. You have a box, say like a box like you have a cuboid, a solid cuboid, and then you cut a V and you put it at this point. So if you put it at this point, it means that water will be flowing through that V, but over the box. So in that case, we would say that our weir is broad crested because the weir is not thin, the material is not thin, it is broad. There is a thickness in the direction of flow. So it flows over the weir, but there is some distance it travels on the actual weir for it in the direction of flow. Now, these two devices on the right hand side, that is picture B, on the right hand side, this is taken from a water treatment plant. So you have water gushing out here from the weirs, so from the notches, whatever you call it. Remember we said the difference is just about the scale. So in this case, in point number B, they are using it to raise the height. They are using it to raise the height. Okay. So the assumptions in analysis is that the velocity of the fluid approaching the weir is considered to be small, so that kinetic energy can be neglected. So that's a simplifying assumption. And also the velocity through any elemental strip depends only on the depth from the free surface. This is almost similar to what we had with the orifices. That's what we had with the orifices. If you take, because the surface is open to the atmosphere, so if you take a streamline through an elemental strip, we'll demonstrate that shortly. So U in each of the elemental strips is given by √2gh. We are going to look at that shortly. So when we say elemental strip, so we mean if you take, assuming say this was a V, okay? Assuming this was a V, so you take any cross section. If you take any cross section, this is the elemental strip you are talking about. So each of these strips, the velocity through this strip is given by U is equal to √2gh. So the velocity through each of these strips is determined by the depth of the water above it. Okay, the velocity in each of these strips is determined by the velocity. The head is determined by the head, which is denoted by h, the head above it. So meaning that the higher the head, the higher the velocity. So a strip that is close to the bottom has a higher velocity than a strip velocity of a fluid at a strip in the bottom has a higher velocity than a strip, near the free water surface, because the only term that is changing in this case is the h. Okay. So consider a horizontal strip of width b. B is any width at a depth h from the free water surface. Okay, this is the cross section on the left hand side. which I put A on the left-hand side, we just have a cross section through a weir. This is a sharp-crested weir. Okay. If you consider a horizontal strip of width B and depth H from the free water surface, now the elemental strip in that case would have a height of delta H because it is along the height of the strip is along the H axis. So velocity through the strip. So velocity through the strip, U is equal to root 2 GH. We say that's the general assumption. If you do not consider the velocity of the approaching fluid. So we say U is equal to root 2 GH. So the discharge through the strip, if we are taking that strip, discharge, we know discharge Q is equal to AV, cross-section area times velocity. So the discharge, which we can denote by dQ, delta Q, that is the small discharge through the elemental strip, is given by cross-section area of the strip. Now, the cross-section area of the strip is given by length times width try to integrate it so that you can come to that. And of course, that is the theoretical discharge. So to get the actual discharge, we multiply by the coefficient discharge.